In our last video for Chapter 4, we're going to introduce a concept that we will get to in more detail later when we talk about Galois groups. Um, well, we'll generalize it a little bit and we'll get to later when we talk about Galois groups. Oftentimes extensions are the same, even though they don't look the same, but they're the same algebraically. The same algebraically means isomorphic. So what is an isomorphism of extensions? What a weird thing. So an isomorphism of extensions. Let's highlight this. Is of extensions, and let's give the extensions names. Suppose we have iota. We'll use the technical definition of an extension where it's a field map. So iota from k to L, and k to k hat, just to keep with the notation of the book. And j from L to L hat is a pair of isomorphisms lambda from k to L and mu from k hat to L hat, such that j after lambda of k is mu after iota of k for all k and k. Now, if you look at this definition, you're immediately irritated because there's so many symbols and so much to unravel. So let me show you how we deal with such definitions as an algebraist. We can represent this definition. So my point is if you're frustrated by what I just wrote, that's fine. I'm also frustrated by what I wrote. We can represent this definition as a diagram. And what's our diagram? Well, we have a field extension, k to k hat. I'm calling it iota. And then we have another field extension, L to L hat. And I'll give you an explicit example here in just 1 second. Okay. What is an isomorphism of extensions? Well, it's a pair. The base fields, the fields that you should be extending, should be isomorphic. That's this lambda. That's from here. And the ambient field, the larger field, should be isomorphic. That's the mu. That's from here. But they can't just be isomorphic. They have to be sort of isomorphic in a way that preserves the other functions involved. So we say the diagram must commute. So we put a circle in the middle. What that means is if we start with one of the sources in our picture, if we view this as a directed graph, this upper left k is a source, and we plug in a k value. Let me use the k. Let's see, what colors do I have? We'll use purple. If I plug in some k and k, and I send it over via iota, and then send that down via mu, mu of iota, that should be the exact same as sending k down via lambda, and then over via j. Those should be the same, and that's how we represent the compatibility, and that's exactly what I wrote in that line there. So it's a very frustrating definition, but the diagram represents that definition. Okay. Let me give you an explicit example, because even the diagram is frustrating without an example. So we saw this field Q adjoin I and root 2. We've seen it the whole chapter. Let's stay with that as our example. And let's let K and L both be Q adjoin I. Okay. So we have Q adjoin I here. We have Q adjoin I root 2 sitting naturally inside Q adjoin I. We have Q adjoin I and Q adjoin I root 2 sitting naturally inside Q adjoin I. So this is just, these functions here are just take P plus Qi and view it as P plus Qi, no root 2's, and no I root 2's. Okay? And the same for the bottom line here. Let's give an interesting function downwards. So here's our two starting extensions. Okay? The horizontal lines are the horizontal functions are the extensions. And the pair of vertical lines will be the isomorphism. But you have to take both of them. Both of them are the data of the isomorphism. We're going to do an interesting function downwards. We're going to let P plus Qi, we're going to send it to conjugation. So that's going to be our lambda. Our lambda, so iota is here. It's just subset. And this is also iota. It's the same function. So J is also iota in our picture. This lambda is going to be conjugation. What must the function going downwards here be so that it matches with conjugation? So let me call this, maybe put a dark purple mu. I'm running out of space here. What must mu be as a function from Q adjoin I root 2 to Q adjoin I root 2 so that it agrees with the previous one? Well, I can tell you what it can't be. You can't send P plus Qi plus R root 2 plus Si root 2. You can't send it to itself. This does not work. It doesn't work because if I go along the top part of our diagram, we should get P plus Qi. But if we go along the bottom part of our diagram, we first take P plus Qi and make it P minus Qi and then send it over. So this cannot work. What we could do, though, is we could make this minus Qi. And that will, in fact, define an isomorphism from this field to itself. It's only conjugate I. That's all it does. So that's one possible choice. Another choice for mu is, well, we can send mu of P plus Qi plus R root 2 plus Si root 2. Well, we have to make sure we negate the I here. That has to happen. And actually, I messed up. If we negate an I here, we should also have to negate it here because there is an I hiding there. Another choice is negate the I, but then also negate the root 2. That's an acceptable thing. We're doing a conjugation in these different numbers we're adding in. But if we negate I and we negate root 2, we have to negate both the I and the root 2 in the product, but that's two negatives. So that's plus I, Si root 2. And that's another choice for mu. So there's sort of two ways which we can complete this to an isomorphism of extensions. There's this first way here, and there's the second way. And in fact, we'll see that that's all the ways. My point with this definition is we're going to come back to it later, but I really wanted to introduce this idea of sort of extending functions, extending isomorphisms. And this is an example of extending the isomorphism lambda to an isomorphism of the larger fields.